Welcome to today's Explainer. I am absolutely thrilled to have you here. Today we're going to unpack some truly invisible yet incredibly powerful chemical forces. We're talking about the fundamental reactions that power our everyday lives, shape our environment, and honestly, might even hold the keys to our future. We are demystifying redox reactions. Let's get right into it. Okay, let's dive into this with a bit of a real-world puzzle. Think about this for a second. What could burning rocket fuel, the slow, destructive rusting of a piece of metal, and that bottle of household bleach sitting in your laundry room possibly have in common? I mean, on the surface, these look like entirely different, unrelated events, right?
Well, here's the fascinating truth. They are all governed by the exact same class of chemical transformation. They are all redox reactions. Whether we're talking about burning fuels for energy, extracting metals, the corrosion of iron, or even massive environmental phenomena like the depletion of the ozone layer, it all falls under the giant umbrella of redox processes.
So, let's start at the beginning. Level 1. The classical oxygen story. To truly understand how this all works, we kind of need to take a quick journey back in time. You see, because Earth's atmosphere is roughly 20% dioxygen, early chemists thought oxidation was strictly about what they could see right in front of them, oxygen attaching to an element, like magnesium burning to become magnesium oxide. They did eventually expand this idea to include the addition of any electronegative element, or the removal of hydrogen, but initially, oxygen was literally the undisputed star of the show. And on the flip side, we have reduction. Classically, this was seen as the exact opposite, just ripping oxygen away. Heat up some mercuric oxide and you drive off the oxygen, leaving behind liquid mercury. Just like oxidation, this definition eventually expanded to mean removing any electronegative element or adding hydrogen. But even early on, chemists realized this golden rule, and this is absolutely crucial for our explainer today. Where there is oxidation, there is always reduction. These two processes, they never ever happen in isolation. They are permanently paired up. If something is gaining oxygen, well, something else has to be losing it. And that is exactly why we smash the two words together to get redox. Moving a bit deeper, we arrive at level 2, the electron tug-of-war. Now, what's really interesting about this slide is the massive paradigm shift it shows. Chemistry is essentially the study of the unseen, right? As our understanding evolved, scientists realized oxygen wasn't the actual driver here. Electrons were. We stopped tracking big, clunky oxygen atoms and started tracking the true invisible actors. Under this new paradigm, oxidation is fundamentally the loss of electrons, and reduction is the gain of electrons. Let's break this down visually with something super familiar, making ordinary table salt, sodium chloride. We can split this entire process into two distinct half reactions. Step 1, solid sodium reacts and actually loses an electron to become a positively charged sodium ion. Because it lost an electron, boom, that's oxidation. Step 2, chlorine gas scoops up or gains those electrons to become negatively charged chloride ions. Gaining electrons is reduction. And this brings us to the agents of our story. An oxidizing agent is the chemical that accepts electrons, while a reducing agent donates them. Now, I know this sounds a little counterintuitive at first glance, but think of it this way. Because our sodium from that last example donates its electron, it's basically sacrificing itself so the chlorine can be reduced. Therefore, sodium is acting as the reducing agent. It helps the other element out. This whole dynamic sets up what is basically a microscopic wrestling match. If you drop a strip of metallic zinc into an aqueous solution of copper nitrate, the zinc is so reactive it literally forces its electrons onto the copper. The zinc gets oxidized, the copper gets reduced. But if you drop copper into silver nitrate, now copper plays the bully and forces its electrons onto the silver. This competitive electron transfer proves that zinc is a stronger reducing agent than copper, and copper is stronger than silver. Fun fact, this exact competition is what allows us to build things like batteries. Which brings us to level 3, the ultimate accounting system. But wait, we have a plot twist. It's super easy to track electrons when they jump completely from a metal to a nonmetal. But what about covalent compounds, like when hydrogen and oxygen form water? The electrons aren't fully transferred there. They're just pulled slightly closer to the more electronegative oxygen atom. It's a partial shift. So without a clean-cut loss or gain, how on earth do we keep track of where the electrons are leaning? To solve this headache, chemists invented the oxidation number. You can think of this as the ultimate financial ledger for chemical reactions, where electrons are the currency. It is strictly a practical bookkeeping system. Even if a bond is covalent and the electrons are just being shared, this system asks us to pretend, just for accounting purposes, that the electron completely transferred to the more electronegative atom.
To play this accounting game, you really just have to learn a simple rulebook. It's honestly just like learning the rules of a new board game. Rule 1. Free uncombined elements always have an oxidation number of 0. Rule 2. Oxygen is usually deeply in debt at -2, unless it's in a peroxide. Rule 3. Hydrogen is almost always +1. And Rule 4. Alkali metals are always +1. The trick is, the algebraic sum of all these numbers in a compound must equal 0 or the total charge of the ion. It is such an elegant tracking system.
Now for the climax of our explainer. Level 4, the 4 phases of redox. Let's move to and see how this builds when we apply our new accounting tool to categorize the chaos of chemistry. First up, we have combination reactions. This is simply where 2 or more elements combine to form a compound. If we apply our new rules to, say, carbon reacting with oxygen gas to make CO2, the elemental carbon and oxygen start at 0. But over in the CO2, oxygen becomes -2 and carbon becomes +4. Carbon is oxidized, oxygen is reduced. That means every single elemental combustion reaction is a redox event. Second, we have decomposition reactions. This is the exact reverse, breaking a compound down into its basic elements. When we split liquid water into hydrogen and oxygen gas, the hydrogen goes from +1 down to 0, and the oxygen goes from -2 up to 0. Just a quick note though, for this to classify as a redox reaction, at least one of those broken down components has to be in an elemental state.
Third is displacement reactions, and this goes right back to that microscopic tug-of-war we talked about earlier. An ion or atom in a compound is swapped out and replaced by another more reactive element. Whether it's a highly reactive metal like zinc bullying copper out of a sulfate solution, or a super reactive nonmetal like fluorine displacing oxygen from water, it's all about a stronger element forcing a weaker one to hand over or accept those electrons.
And finally, the 4th phase. This one is a fascinating chemical paradox called disproportionation. It's a special type of redox reaction where a single element, acting as a reactant, is simultaneously oxidized and reduced. It literally splits its chemical identity into both higher and lower oxidation states at the exact same time. No way, right?
And this brilliantly illustrates how that works. Look at the breakdown of hydrogen peroxide, which is basically the household bleach we mentioned at the very beginning. The oxygen inside starts at an intermediate -1 state. When it decomposes, some of that oxygen forms O2 gas, moving to a 0 state, which is oxidation. But the rest of the oxygen forms water, moving to a -2 state, which is reduction. It's one element mathematically splitting in 2 directions at once.
Which brings us right back to our central anchor, whether we're looking at the old-school 18th century classical transfer of oxygen atoms, or we're using our modern, highly sophisticated financial ledger of oxidation numbers. The balance of the universe is always maintained. The math always zeroes out. Where there is oxidation, there is always reduction.
And that leaves us with a pretty profound thought to wrap up today. We know for a fact that redox reactions are responsible for the destructive corrosion of our infrastructure, all that rusting metal. But as we've seen, environmental solutions like the development of liquid hydrogen as a clean fuel, the so-called hydrogen economy, they also fall squarely within the realm of redox phenomena. So if we can master this invisible electron accounting system, could it be the exact tool we need to save our planet? Think about that the next time you see a rusty piece of iron. Thanks so much for joining me today to explore the hidden logic of chemistry.